One day there was a fire in a wastebasket in the office of the Dean of Sciences. In rushed a physicist, a chemist, and a statistician. The physicist immediately starts to work on how much energy would have to be removed from the fire to stop the combustion. The chemist works on which reagent would have to be added to the fire to prevent oxidation. While they are doing this, the statistician is setting fires to all the other wastebaskets in the office. "What are you doing?" the others demand. The statistician replies, "Well, to solve the problem, you obviously need a larger sample size." And we're going to be talking about sizes of samples and what is a sample. So first of all, one of the ideas, the first idea is to draw a sample. We want to know about an entire population, but it's not possible to ask everyone. It's just impractical or even possible. So the idea with the samples, we're just going to get a smaller group of individuals from the population. All right. You do this every day. For example, suppose you wonder how the vegetable soup you're cooking for dinner is going to go over with your friends. How do you check? Well, you can just take a taste. And it's hard to go a day without hearing about the latest opinion poll. These are examples of sample surveys. So, how can pollsters claim that a sample is representative of the entire population? Well, the answer is that professional pollsters work quite hard to ensure that the taste, that the sample they take, represents the population. If not, the sample can give misleading information. So some examples of sample surveys are cooking, friends' opinion, and of course, opinion polls. Now, one thing we want to be really careful about is bias. When a sample doesn't represent every individual fairly. So it's harder to pick a sample from a population than you think it is. They usually fail because they overrepresent or underrepresent parts of the population. The method might overlook subgroups that are harder to find, such as the homeless or people who only use cell phones. So sampling methods, by their nature, tend to over or underemphasize some characteristics, and that type of sampling method that does that is said to be biased. So here's a famous example, Roosevelt versus Landon. And the Literary Digest mailed more than 10 million ballots. And the results were, okay, Alf Landon is going to definitely be the next president. Landslide vote, 57% to 43%. And of course, we all remember President Landon, or do we? In fact, so there's Landon on the right and Roosevelt on the left. Landon only took the 2 states in red. Roosevelt won 62% to 37%. The problem was that the sample they took was not representative. They created their list of 10 million people from the phone book. Well, back in 1936, let's see, the Depression had already hit. There were lots of poor people, and not everybody owned phones. So the problem is they were oversampling the richer people compared to the poorer people, and Roosevelt was appealing more to the poorer people because of the economy. So another example would be is if we polled the football team and the band on which was better, sports or band, do you think you'd get different results than if you polled just random students in the cafeteria? So bias is the bane of sampling, the thing you have to avoid above all else. And there's usually no way to fix a biased sample and no way to salvage useful information from it. So if you get a biased sample, you get to start over. So you can't fix them. So here are 3 sources of bias in any sample. You have to be careful about selection bias. So some part of the population is systematically excluded or underrepresented. So say we decide to sample the residents in an apartment complex about putting in an exercise facility in the complex, right? So we're like, okay, we might raise the rent, but we're going to put out this beautiful gym. Well, selection bias, maybe we decide just to sample the bottom floors because we don't want to take the stairs. Our sample might have more older individuals or families because they have a preference for lower floor apartments. So we may leave out the younger people who don't mind taking the stairs with their groceries, and those might be the people who really want to know about the gym. Another thing we could do, another type of bias is measurement or response bias. So the measuring process systematically distorts the data. So what does that mean? In the apartment example, we could put a survey like in the main office and say, hey, are you interested in us putting in a gym? Well, who's going to respond to that? If you don't really care, you're probably not going to respond. So your results will be exaggerated. Or maybe you word the question in such a way that it kind of leads to certain results. And I like this cartoon. How would you rate the king's job performance? Would you say he's doing a good job, an outstanding job, or a terrific job? And he responds, I think I know who is paying for this poll. So you can do the same poll with me. If you think I'm doing a good job, an outstanding job, or a terrific job, please let me know. I think I would have a response bias. There's also non-response bias. So when we miss certain people, and the people we missed that we don't get data from, they might be different from the other people. A good example is, let's say we sample the apartment residents only during working hours. Well, then we've left out everybody who's working because they're not at home. And maybe they would have a different opinion about the gym. So one thing we want to do in our sample is we want to randomize. So that's the best way to avoid bias. It protects us from the influences of all features. So a nice way to think about it, let's say we added salt to the soup, but we didn't stir it before we tasted it. Well, the taste isn't going to be exactly right because you have some part that's really salty and the rest that needs salt. So you need to stir first so you can randomize the salt. It's the same idea for samples. So we're going to deliberately introduce some randomness so that our parameters are going to be better. So it protects us against things that we know are in the data, and it can also protect us from things that we don't know. So on average, a sample looks like the rest. It protects us from bias, and it makes it possible for us to draw inferences from a sample. Now, you might say, well, what is an inference? That's the act or process of reaching a conclusion about something from known facts or evidence. In geometry, you could say, well, we could make a conjecture based on what we saw. So if you want to say, okay, in general, the residents of the apartment do want a gym, well, or maybe they don't. You would be inferring that from your survey. And these inferences are the most powerful thing we do in statistics. And it's all made possible because we're going to deliberately choose things randomly. Okay? So sample size does matter. And we're really going to get into some of the details of, what number sample size we're going to do. For the moment, you do need to know that you don't want to just sample, one. Like the joke with a wastebasket. We don't want just one wastebasket on fire. Sample size matters. And we'll give you some general guidelines later. The size of the population doesn't matter. Believe it or not, if I wanted to do a sample with 100 students at Cedar Ridge or 100 people in Round Rock, that's not going to matter so much. And usually the fraction of the population doesn't matter. All right? So it doesn't matter if I do a fourth or a third or a half. Well, actually, I'm sorry. Let me take that back. It doesn't matter if I do 2% or 3% or 5%. I don't want to do a fourth, a third, or a half because these are all more than 10%. And why is that? Well, think about it like you're doing the soup, all right? And you have a pot just for you and your friend. And when you do the sample from that, you're just checking to see if the soup's right. Okay, the next time you make soup, you're having a big party in a big pot. Do you need to take a bigger sample of that big pot, or was the sample you took before that sample size appropriate? Well, if everything's mixed and randomized, it's fine. So maybe you could say, well, I don't really feel like doing a sample. Let me just ask everybody. Why bother determining? So we could do everybody, and that would be a census. Well, why should we do a census or a sample? Well, sometimes it's almost impossible to do a census. I could ask every person at Cedar Ridge. A census there would probably be easier. And in a way, we do censuses here at Cedar Ridge when we make every student fill out a form. But if I wanted to get everyone in Texas, that's a lot of work, and some people might hide from me. So it's very difficult to get a census. And that's probably part of the reason that we only have censuses in the United States every 10 years. So some other things you should know, we have populations and parameters. So we're going to use mathematics to model what's going on. And parameters are the key numbers in those models. If the parameter is part of a model of a population, it's called a population parameter. And we can use data to estimate population parameters. So anything we find from the data is a statistic, or it could also be called sample statistics. So when they estimate population parameters.